We're going to have Zach and Cody are going to stand in the aisles with microphones. And so if you have a question, we ask that you come to the aisle and line up next to them, and we'll just alternate back and forth. We're sorry to make you move, but that steps on fewer toes than if we move in between all of you trying to get you the microphone. So we'll just take questions if you want to come to the microphone or if you want to go up to them. Please don't. Just come and line up in the aisle right next to them. Go ahead, over here.
Hi. Thank you. The gravitational waves and the light waves are traveling at the same velocity. Why is there 1.7 seconds difference?
You were listening.
Who's going to get this one?
You go ahead, or whoever.
I get this one? OK. Actually, there is a topic of hot debate in the field yet. So I would say that not the entire community would agree with the same answer. So one possibility is that it takes some time for the two neutron star to launch the jet. This seems to be quite unlikely. The other possibility is that the jet forms right away, but it takes some time to break through the material that the merger created. So you have the merger, it comes all together, you form the jet, but it takes some time for the jet to get out. A third explanation that you will find is that we are not looking down to the jet, we are a little bit off axis, and that's the time it takes light to reach your line of sight. So maybe a combination of these three.
Can I add one thing? As a general comment, you know how 5 minutes ago I told you how all these theoretical astrophysicists made predictions and these observations have confirmed them? Well, I kind of lied. Well, the big picture has been confirmed. But this question you just asked, it's a hot debate, is an understatement. The problem is we don't really understand why there was that much of a long delay. 1.7 seconds in these astronomical terms is a very long delay. This is a very hot debated topic. And in fact, the observations that Wenfei and Rafaela are making and through X-rays that are going to come out again behind the sun in next week, could give us the answer for why this long delay is coming. But this was not widely predicted. It was an unexpected mystery, so we have some open questions.
There's still time to come back and work with them and figure it out, right?
Yeah.
Other questions? Do you have a question? Yeah, right here.
How many gravitational wave observatories, is there going to be a maximum number of observatories that will be built? As far as I understand, there are 2 more that are in development. There's going to be 1 in space. But I'm just curious, there's dozens and dozens and dozens of observational observatories. Will there be a maximum, a limit to the number of gravitational waves?
OK, so let me start by telling you what is happening now. So there are the LIGO detectors, are 2 detectors. One is in Washington State and one is in Louisiana State. And we started, the LIGO observatory started with 2 detectors, and that was the absolute minimum we needed to be certain that we are detecting gravitational waves and not some random noise on the Earth. The way we detect gravitational waves is connected to figuring out that mirrors are being shaped by gravitational waves that are arriving on Earth. But of course, mirrors on Earth can be shaken by all kinds of other things. So having 2 observatories is one of the ways, not the only way, but one of the ways that ensures that it's not some random shaking in one location. So if it's a cosmic signal, it has to have the same characteristics in the 2 locations. And it's not some local random noise. So we needed 2 observatories for this reason. There is a 3rd detector, which is now operating, and we collaborate with the European detector called Virgo in Italy. It's a French, Italian, Spanish, and Dutch collaboration. And the event that was detected 3 days before the binary neutron star that actually my graduate student Eve Chase led a lot of the work for that binary black hole detection was the first signal that was seen by 3 detectors. The 3 detectors allows us to localize things better on the sky, which is obviously very important for electromagnetic observation. Yeah. There's a plan, and an active plan, and one of the Northwestern faculty might end up being connected to that. But there's a 3rd detector in India being now under construction. There's a Japanese detector being under construction. So we're talking now 5 detectors. Whether we're going to get more will depend on whether more countries will get involved with gravitational wave astronomy. And of course, it depends on funding. And these are big projects. And what we will need to have is either bigger detectors, underground detectors, and more spread out on the Earth. But what we will also need is to cover the spectrum of gravitational waves the same way we have covered the spectrum of electromagnetic waves, from gamma rays to radio through X-rays, optical, and infrared. And that we can only do if we fly a gravitational wave detector to space, which Shane is particularly involved in. And that will allow us to see gravitational waves from supermassive black hole mergers. That there is no way to detect those gravitational waves on the Earth. Those are very low frequencies, and the whole Earth is basically seismically moving, and there is no way to see those frequencies on the Earth. We have to be in space, just like there's no way to see X-rays on the Earth because the atmosphere is blocking them. So there is a lot of reason and scientific motivation to have more detectors and different detectors.
I think we have one on this side.
Hi, this may be for Professor Fong. I believe you have a fairly large number of gamma ray bursts every year. Is there anything about the characteristics of this gamma ray burst which is tied to the gravitational wave that would allow you to identify previous gamma ray bursts and tie them to possible gravitational wave?
Oh, yeah, that's a great question. So, right, so for the past several decades, we've detected lots of gamma ray bursts from these gamma ray satellites, and they've mostly been very bright compared to this gamma ray burst. So, and we think the reason is because basically that movie showed that it launches this collimated jet of gamma rays, kind of like a fire hose of material just pointed directly at us. And so we think that with the gamma ray bursts we've detected in the past, we've been staring straight down the barrel of the jet, and it's been very bright. That's where the gamma ray emission is brightest. Whereas this gamma ray burst, because it was detected by gravitational waves first, that jet of material could be pointed anywhere it doesn't need a very strong gamma ray signal to be detected in gravitational waves. And so this was actually particularly weak in terms, it was quite faint compared to these other gamma ray bursts that we've seen. But we were able to see it because it was, one, we had the help with the gravitational wave signal. We were able to look at the gamma ray data more carefully. And two, because it was very, very close. So it was about, I don't know, at least 100 times closer than the closest gamma ray burst that we've ever seen before. So it was extremely close. We were able to see this very weak signal. So this has really mobilized the community to go, the gamma ray community to go back and look and see, have we seen these other little blips before in our data? Maybe they were kind of hidden, weak, nearby gamma ray bursts. So that's definitely still an open question in astronomy.
And that's an important point to punctuate, which is these observatories that are tiling the field and taking all of this data keep the images. And so when there's such an event as this, we can go back and look through past data to see if we see, that's what she was referring to.
Yeah.
And so there's decades and decades of work that can happen even after the images have been taken, because they're all stored and can be looked at with a new lens once you have new information.
Right.
That's a good point. I think we're going to go this side one more time because I counted over here. Then we'll get back to one on each side.
Zach, there's...
Hi. You mentioned gamma rays and this gamma ray burst. Is that the cutoff? Like, in other words, what about cosmic rays? Mm-hmm. Are those detectable?
Yeah. So you don't detect the cosmic ray by itself. You detect the shower that it creates. So when the cosmic ray interacts with the atmosphere, it sort of creates a number of charges that we can detect. So yes, definitely yes.
And did we see cosmic ray showers from this event?
No.
Okay.
No.
This side? Do you have people? We're not lining up, so I'm not sure I understand where there are questions. So if you can help us out, that'd be great.
Thank you. Why is it we call them gravity waves as opposed to space-time waves?
Oh, that's your question, Vicki.
That's my question, yes. So actually, gravity, so we call them gravitational waves and not gravity waves. And gravity waves are more like the waves in the ocean, that of course the gravitational force has, drives them, but they're not the waves associated with space-time. So gravitational waves could also have been called space-time waves. I agree with you. But for some reason, we stuck with gravitational waves as the terminology. And I'm turning to Shane because he tends to know more of the history of science than I do.
Einstein's first paper was actually called Gravitational Waves in German, if you go look at it. So he's the one who gave it that. The term space-time actually came a little later. This understanding that space and time are together was slow in emerging from the development of relativity. It's largely due to Einstein and Minkowski and Lorentz and people like this. But I think initially, in these early days, there was no standard nomenclature for this. And so, what Einstein said stuck, because he was Einstein, right? And so we just, astronomers are slow to change. There's a lot of things in astronomy we should change that we've never changed, and this may be one of them, so.
Cody, there's one here.
Could you talk just a little bit about the cohesiveness in the astronomy family? You seem to take it for granted, and I just don't understand why and how it works there and it doesn't work elsewhere.
You fooled them well.
I will.
No, I'm teasing.
So I'm happy to take this question. It's not as cohesive as it may appear. But at the same time, science across all science, we realize that it has become bigger and bigger. Okay, science right now is a team sport, I say. Okay, and it's no longer one scientist and one student in an office, pencil and paper. Okay, that science is long gone. Maybe it still exists in mathematics, but that's about it. So the LIGO scientific collaboration, for example, alone is more than 1,000 people. And it's a challenge in itself. We have been studied by social scientists for how we work and how we actually manage to make progress. And we do make progress. We opened a brand new field in astronomy. And now with this event, we came together, the LIGO scientific collaboration works with the Virgo scientific collaboration, which is in itself 2 separate collaborations. And now these 2 collaborations worked with the electromagnetic community, which is not a cohesive collaboration in itself. It's about, we worked with 70 small teams. Each team was somewhere between 100 people and 5 people. And it was a challenge. And to not acknowledge this, I think, is not fair, okay? It's not all roses, and it was definitely difficult. We published all together close to 4,000 authors, a paper where we told the story of the full discovery, from gravitational waves all the way through the full electromagnetic spectrum. And 11 people wrote that paper in terms of physically, writing every sentence. I was one of the 11 people. But of course, it was written with input from all these 70 teams and the 2 gravitational wave teams and the 2 Gammaray teams. And I think I grew old 5 years in those 2 months by being on the writing team. And, but I also learned a lot, both scientifically and as a human. And it made us all better as scientists. And next time we're gonna be better at doing exactly that. And it is a social sport. It's a team sport. And at the end, you know what kept us going? It's the paper we're gonna be proud of. At the end of our lives, it's the paper we're all gonna be proud of. And we kept saying every time we reached the wall and we had disagreements, and some disagreements were important and some were petty, because we're humans. We're all like the rest of you. And what we said is that we have to write this paper, no matter how difficult it is, to struggle with our egos and how this sentence reflects on me or you, etc. We have to write this paper because this is a historic discovery. And we wrote it through long nights and long fights and lots of smiles. And then at the end, we were all proud of it.
Yeah, it's a good story, good question. I think we have time for 2 more questions. So we'll take one from each side. Who's going where? Go ahead, you pick where you're headed.
Thank you very much. The signal duration of 100 seconds seems very significant. Had it been 25 seconds or 50 seconds, how would things be different?
So the length of the signal tells you something about how massive the 2 objects that are in spiral going one around the other are. So the massive black holes we detected 2 years ago, the length of the signal was only 0.2 seconds, a fraction of a second. But the signal to noise ratio, so how significant, how loud the signal is in our data, can be still very high even if the length of the signal is very short. So the 100 seconds, when we first got the signal and we could tell it was 100 seconds, it told us very quickly we're dealing with neutron stars. But the signal to noise ratio, which tells us how loud is the signal, how important, how bright, in electromagnetic terms, we would say, how bright is this star on the sky, is this source on the sky, it doesn't always correlate with the length of the signal. Now, this particular source, the binary neutron star, was the brightest, the loudest gravitational wave source we had seen, even louder than the very first gravitational wave signal we received back in 2015.
One last question over here somewhere.
Is it possible that gravitational waves contain more complex information? Do they carry complex information about the local area where they came from and also the objects in the way as they travel toward us, such that we might be able to use them to make maps of deep space maps of the sky?
That's a great question. So, so there's actually 2 parts to your question. So let me first take the first part. Do the gravitational waves carry information about the origin, the local region from where they were produced? So that's very close to where the 2 neutron stars were inspiraling, or the 2 black holes are inspiraling and coming together to form a single black hole. And the answer is yes. So the gravitational waves do carry more information about how distorted the space or space-time was right around the region of the 2 black holes. And we can extract more information depending on how loud the signal is, so it goes back to how the signal to noise ratio question. And so far, we do examine the signal in great detail from this point of view. And we ask the question, is this information imprinted in the waves consistent with what Einstein predicted based on his theory of general relativity? And so far, the answer has been, for all the signals we have detected so far, is that it is exactly the way Einstein predicted space-time should behave, very close, highly disturbed space-time, very close to the two black holes or the two neutron stars. So no deviations from Einstein's theory. The second part of your question is, does it tell us something about the space between the source and us? And actually there, the answer is not much. And the reason is that gravitational waves have this property of they don't give a damn about what they go through, okay? And that's what makes them so hard to detect. So they don't get impeded, they don't get blocked by anything, and if they don't interact with things along their way, they carry no information about the things along their way. But that's what also makes them hard to detect, because they don't interact much with our detectors, and therefore it's hard to detect them. So we don't get much information about the space in between.
Thank you. Good question. Well, I hope you've enjoyed this conversation. I think we've learned a lot about the teamwork involved in these discoveries, about the fact that there's still plenty to do, that we are still working on it, and that it can become something that is becoming a routine aspect of astronomy, which is learning more about the universe through these two ways. So join me in thanking our panelists.
Thank you for coming.
Thank you all for coming tonight.